Okay, we're going to discuss sigma bonds and pi bonds in a bit more detail, and we're going to use our molecule C2H4, which is also known as ethene, as our model. The Lewis structure for ethene looks like this, where you have two carbon atoms connected by a double bond, and then each carbon has two hydrogens connected to it with a single bond. And it turns out that the single bonds between the carbon and the hydrogen, those are all sigma bonds. And that's always the case. Single bonds are always going to be sigma bonds. And then the double bond here, that consists of one sigma bond and one pi bond. Now, to review how to tell the difference between a sigma bond and a pi bond, first we're going to let's just look at this sigma bond between this carbon and this hydrogen. And we'll write it like this. We're going to draw the connection between the carbon and the hydrogen. And then I'm going to draw one of the sp2 hybrids that comes off of this carbon atom. Remember, there's two more over here. There's one here, and there's one here, like that. And then we're just going to go ahead and we're going to put on the 1s orbital and that on the hydrogen atom, and that overlap between that 1s orbital and the sp2 hybrid on the carbon, which I'm going to color here in red, that's going to represent the basis for the bonding. And we can tell this is a sigma bond because what you do is you take the center of the two atoms involved in the bond, so the center of the carbon atom and the center of the hydrogen atom, and then you imagine drawing a straight line between those two centers. And as I do that, you'll notice as I draw a straight line between these two centers, that straight line goes through the overlap that's formed between the two orbitals. And anytime you have that, you have a line between the two atoms that goes through the overlap, that's going to be a sigma bond. So it's going to be important to remember that it's the overlap of the orbitals that causes, or that's responsible, I should say, for the bonding. Now in this double bond here between the two carbons, let's go ahead and draw the first bond between those two. So you got a carbon and then another carbon. And I'm going to go ahead and draw one of the sp2 hybrids coming off of this carbon over here. And then I'm going to draw the other sp2 hybrid coming off of this carbon right here. And when you draw both of those, you see that you get significant overlap between the two orbitals, the sp2 hybrid orbitals. And it's that overlap that forms the basis of the bond. And once again, if we draw a straight line from through the center of this carbon atom through the center of this carbon atom, we see that when we do that, the lines drawn between the two goes through the overlap between the two atoms, and that's going to form the basis of the sigma bond in the double bond. Now, what's the deal with the second bond, the pi bond? Well, in this case, we have to remember that both those two carbons in an sp2 hybridized carbon, this is formed from the overlap of an s orbital and two p orbitals. So that's going to form three sp2 hybrids. But there's also another p orbital that is unhybridized that's left over, and that sticks up and down out of the plane of the paper the way this is drawn, like this. Now, if I'm to rotate this molecule, so we're looking at it, straight up and down this way, then it's going to look like that p orbital is going to sit this way. And on the second carbon, that p orbital is going to look like it's going this way. And there's the overlap. It's a side-on overlap. It's kind of goofy, but that's what's going on. So here's your p orbital, right? The p orbital is sort of that peanut shape. And that's centered on the atom. And so you get overlap here, and you get overlap here, and it's that side-on overlap that's the basis of the pi bond. And we can tell it's not a sigma bond because if we draw a straight line between the two atoms involved in the bond, look at that. That straight line does not hit any of the overlap in the orbitals responsible for the bonding. And so the second bond in a double bond is always going to be formed this way, and it's going to be a pi bond in that particular case, where the overlap does not fall in the straight line connection between the two atoms involved in the bond. Now I want to go into this a little more deeply. So let's imagine we're looking at this overlap here between two carbon atoms we're going to look at the, here's one of the carbon atoms, or a representation of it. Here's one of the sp2 hybrids. Here's another sp2 hybrid and another sp2 hybrid. That's one of the 3 sp2 hybrids on our first carbon atom. And then these black foam pieces will just represent the sp2 hybrids on the second carbon atom. And we can envision bringing these 2 carbon atoms close together and seeing an overlap. See the overlap between the 2 sp2 hybrids. That's going to form the sigma bond of the, involved in the double bond between the 2 carbons. That's the first part of the double bond. And what we can notice is I can actually rotate this carbon over here relative to the other one. I'm freely spinning around that sigma bond. And as I'm doing so, the overlap between the 2 orbitals remains consistent. And that means that I can get free rotation around a sigma bond without breaking the sigma bond. Hopefully that's pretty easy for you to see. Now we're going to try the same trick here with a pi bond. I hope you can see if you rotate this, if you rotate around a pi bond, you don't get the same thing. Rotation around a pi bond actually causes a breaking of the overlap between the 2 atoms involved in the bond. So here I've got these 2 carbon atoms, so to speak, stuck close together, and you can see the overlap of the orbitals. So we've got the overlap above and below the carbon-carbon connection. And now, though, if I rotate here, if I rotate one relative to the other, the overlap disappears. It snaps. The bond, the overlap, is broken. And so you do not get free rotation around a pi bond. If you want to rotate around a pi bond, you actually have to break the bond and remake the bond. And that has some serious implications that we're going to see here. So I'm going to draw 2 chemical structures here. The first one, they both look a lot like ethene. This one here has got, this is going to look like ethene, but instead of putting 2 hydrogens down here, I'm going to put a chlorine atom here and a chlorine atom here. And we'll call this structure A. And then over here, we're going to do the same thing. We're going to make it look almost like ethene again. But in this case, I'm going to stick chlorines, rather than putting them on the same side of the double bond as I've done here, I'm going to put them on opposite sides of the double bond, such as I've done here. And what we see is if I want to rotate this carbon atom, I want to rotate it like this, like that, so that this hydrogen atom gets rotated up here to where this chlorine atom is, and then this chlorine atom gets rotated over here to where this hydrogen atom is. If I was to do that, I would actually end up breaking the pi bond. And so we can ask ourselves, can I convert structure A to structure B by rotation around this bond, around the double bond, without breaking the bond? And we just saw the answer is no. You can't do that. And because you have to break a bond and remake the bond to go from structure A to structure B, these are actually different molecules. You have to go through a chemical change to go from structure A to structure B, or from structure B to structure A. And because of that, these are actually 2 different molecules. They act similarly, but they have different boiling points, they have different melting points, and they have different chemical properties. And we've got to give them different names. Now, we could call them both dichloroethene. Actually, we'd have to call it 1,2-dichloroethene, both of which have the formula C2H2Cl2. So they have, in this sense, they have the same name and they have the same chemical structure. Well, that can't be because they're different things. And let me go ahead and explain why this is the naming system here. We use ethene because they're both derived from this molecule here, which we called ethene. We call them both dichloroethene because there's 2 di meaning 2 chlorine atoms attached. And it's called 1,2-dichloroethene because one of the chlorines is attached to the first carbon atom and the other chlorine is attached to the second carbon atom. Now we can't, like I said, we can't just call both of these 1,2-dichloroethene because they're different molecules with different boiling points, melting points, and chemical properties. So what we do is we call this one the cis form, because the chlorine atoms are on the same side as the double bond, cis meaning same, and we call this one the trans form. The trans. So we call it because the chlorine atoms are on opposite sides of the double bond. And so we've given these different names to indicate that they're different molecules. And these are examples of what we call isomers. Isomers are molecules that are going to have the same chemical formula, but they have different orientations of the molecules in space. And in this case, we end up having the cis and trans form of 1,2-dichloroethene.